Hi, everyone. Um, if I was late to section this week, I apologize. I have been not having the greatest amount of sleep lately. So, for anyone who left early because I didn't show up, I'm going to record a little mini lecture on some of the stuff we did. So, let me log in with my tablet and we'll go ahead and get started. This is, of course, optional because it's my fault that I missed. Okay, so here we go. Cool. Okay, so I'm going to share my screen. One of the things we talked about was, I believe it was homework 21, problem 6, which is not especially difficult, but it's kind of tedious. It asks you to find the derivative of 1 plus x squared over 2 factorial. Okay, and you guys may not have seen factorials in a while, so these exclamation points might trip you up. So let me remind you what that means. We have that in general, put a little box over here. For any number n, if I want to compute, I should say for any whole number n, if I want to compute n factorial, it ends up being n times the integer less than it, so n minus 1, times the integer less than it, times so on and so forth, until I exhaust all the integers and I get down to 1. Okay, so for example, we could compute each of these things that appear inside this derivative we have to calculate. So 2 factorial is just 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. Okay. And each of these I could compute. So that's 2, this is 6, this is 24. A nice pattern you might notice is that, okay, for 5 factorial, I have to compute 5 times 4 times 3 times 2 times 1. But this is the same as that. So in actuality, 5 factorial is just 5 times the factorial that came before it. And we know 4 factorial is 24 from above. So 5 times 24 is 120. Okay, so that saves a little bit of computation time. Luckily, we don't have to go any further than 5 factorial. But okay, so I could replace all of these fractions here. And instead of writing factorial, okay, we know 2 factorial is 2. So that's just x squared over 2. 3 factorial is 6. So that's x cubed over 6. 4 factorial is 24. 5 factorial is 120. So I could write it like that. And then to take a derivative here, we can just go term by term and take the derivative. So derivative of 1 is 0. Derivative of x is 1. Derivative of x squared over 2. Okay, well, this is going to get a little bit complicated if you don't know a trick. So I'll write a little trick here. What you have to keep in mind is that, let's say I'm taking the derivative of x to the n divided by c, where c is a number and then n is some power. The one thing you have to keep in mind is this is the same as, instead of writing xn or x to the n over c, I could have written that as 1 over c times x to the n. And 1 over c is just a constant. So that's not going to affect the derivative. I can pull it outside. And then by our usual trick with power rule, we know that the derivative of x to the n is nx to the n minus 1. Okay, and then I could put this all as a fraction again if I wanted to. Nx to the n minus 1 over c. Okay, so that's a little note to ourselves. The important part is, if you're taking a derivative of this thing, it's kind of the same as just taking the derivative of the numerator and rewriting whatever the denominator is, because the denominator is just a constant. In effect, you can pull it outside, focus on the main derivative, and then put it back when you're done. And the short way to think of that is coming back over here, derivative of x squared over 2 is the derivative of x squared, 2x, and then I just divide by 2. So the denominator stays. Same story here, x cubed. When I take the derivative, becomes 3x squared. And I just leave the 6. Derivative of x to the 4th is 4x cubed, and I just leave the denominator. And same story for the last term. Okay. I think you can plug that into WebWork and it'll accept it, but I want to simplify. So the 2's cancel in that term. 3 over 6 is the same as a half. So that's x squared over 2. 4 over 24 is 1/6. So that's x cubed over 6. And this will be x to the 4th over 24. Okay, so now's a good time to pause the video after you hear what I'm about to ask. What does this, or rather, what do these denominators look like? They should look familiar. Pause the video if you need a second. They look exactly the same as our factorials. So that was, oops, okay. 2, 6, and 24 are exactly 2 factorial, 3 factorial, and 4 factorial. 2, 6, and 24 are those. So I could have written this as 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. Okay, next pattern recognition question. Does this look like anything familiar? So pause the video if you need a second. Okay, we're back, and it looks exactly the same as what we started with, except for the last term is different. So we started with this plus an extra term of x to the 5th. And that is what we end up with, right? Basically, the only term that went away was the x to the 5th over 5 factorial. Okay, so hopefully that's surprising and interesting. And the next question I could ask is, what other functions does this work for? So here we're saying we took, let's call this f. I had some function f, I took its derivative, and I got, or well, I almost got the exact same thing back out. The function almost didn't change after taking the derivative. Okay, so I put a little almost over the equal sign. What function do you know where this is exactly equal? Pause if you need to think. The function that works for that is e to the x. We know that if I put e to the x in here and I take the derivative, it doesn't change. Derivative of e to the x is e to the x. Okay. So my guess is there's something intimately related between these two functions, between this kind of chaotic looking thing, 1 plus x squared over 2 plus blah, 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 and e to the x. So I'm going to erase this screen and I'm going to go to a Desmos plot that I want to show you guys. So pause the video if you need to. I'm going to come over here, share my new screen, bear with me. Okay. Great. So here's Desmos, just a little graphing tool. And I have two functions that I've written in here. Or, well, I have some more complicated things, but we're just going to focus on the red and the blue graph to start with. The red graph is just e to the x, right? That looks familiar to you guys. The blue graph is a little more complicated. I have it written as a sum from k equals 0 to n of x to the k over k factorial, okay, which maybe looks like nonsense. So let me just write out what that is. If I pick k equals 0, I would get x to the 0 over 0 factorial. Okay, you might not recall, but x to the 0 is 1, and 0 factorial is 1. So it's actually just 1 divided by 1, which is 1, of course. Okay, so the first term is 1. Second term, if I set k equal to 1, so I'm just incrementing k, would be x to the 1 over 1 factorial, so that's x. Then I would get x to the 2 over 2 factorial, and then x to the 3 over 3 factorial. And it would keep going. Okay, so that's a nice shorthand for writing what we were just working with, basically. Except it goes however high you want it to go. I can set n to be 25 instead of just 5 if I wanted to. And Desmos will plot it for me. So let's see what happens if we do that. So down here, I have at the bottom, I have a slider for n. Okay, so I could grab this slider and let's push it up to 3. Okay, so that would be the cubic polynomial if I got the third term. And then if I add x to the 4th over 4 factorial, if I add x to the 5th over 5 factorial, n equals 5 gets us there. And what you might notice is that these things are getting really close to one another before they like diverge and stop being close to one another. But they're starting out pretty close. And okay, I could keep going. Let's try, what if we had a 6th term, and a 7th, and an 8th, and a 15th, and a ton of terms, right? And then all of a sudden, you can't distinguish between these two. So I'll turn off the blue plot. Here's e to the x. Here's my sum of 25 terms. Here's e to the x. Here's my sum of 25 terms, right? They're exactly the same on that interval before they end up diverging, right? So e to the x stays close to 0, and this will decay really quickly to like negative infinity. But if I went higher than 25 terms, it would keep wiggling back and forth and take up more and more of this number line. So if I set this to 100 or something, right, and I activate my animation abilities. Okay, so let's go back to n equals 3 and then animate. Look at that. The more terms I have, the better it gets, sort of thing. Cool. So that's pretty interesting, I think. I'll set this back to 25. Okay, and we'll put it back on. Let's put it on 1. For 1, it's a terrible approximation. It's just a line, but at least they agree at one point. Oops, didn't mean to warp that. Okay, good enough. So what that tells us is that this function is actually equal to e to the x in the limit. Okay, so dot, 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 if you keep going, that equals e to the x, which should be mind-blowing. But it should also make sense in the sense that we know the derivative of e to the x is e to the x, and we know the derivative of 1 plus x squared over 2 factorial plus dot, dot, dot is 1 plus x squared over 2 factorial plus dot, 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 right? In the sense that, okay, when I cut this off at the 5th term, we lost a term when we took the derivative. But if I keep going to infinity, there will always be more terms to have, and I essentially don't lose anything. Okay, so that's fun. And then I just want to show you guys some other pretty pictures. So let's forget about this function in blue, and let's instead think about one of these other functions that I have here that look more complicated. So like h1 or h2. Let's just turn on h1. Okay, again, I have n set to a very small number. So right now n is at 1, and let's figure out some terms here. So if I wrote this out, so start with k equals 0, okay, negative 1 to the 0 is 1, x to the 2 times 0 is x to the 0, which is 1, and then 2 times 0 factorial is 0 factorial, which is 1. Okay, so starting out, we just get 1, so that's fine. If I set k equal to 2, well, negative 1 squared is positive 1. Or sorry, if I set k equal to 1, that's what I should do. Then I get negative 1. Okay, so let's write this out. I would get minus x squared over 2 factorial. And then if I set k equal to 2, I would get, okay, negative 1 squared is positive, and then it would be x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And again, I'll ask for what pattern you see. So pause if you need a second. The pattern you should see is, first, it's alternating, plus minus. And second, these are all even powers and even factorials. But other than that, it looks pretty darn similar to e to the x. E to the x was just, it was positive everywhere, and it had, x over 1 and x cubed over 3 factorial and x to the 5th over 5 factorial. But it's sort of like the even component of e to the x, I guess I could say. How do I erase really quickly? I don't know. Okay, that's fine. So it's like the even component of what we worked with a second ago, but it's alternating, right? It's not all positive. It switches plus minus, plus minus. So let's see what that does. Oops, stop annotation. N equals 2 gives me that. N equals 3 gives me that. 4, 5, 6, 7, 8, up to 25. Pretty wacky. I like to think I'm like bending metal wire, and as I go further and further out, the wire like cools in this section so it stays rigid, and then it keeps going, it keeps going. And the more I bend it, the more it stays in place. And eventually, if I take infinitely many terms, this kind of cyclic pattern continues. Does anyone know what that function is? Take a second if you need it. It's actually the cosine function. Okay, so you guys don't end up doing much trig in this class, or any trig, I don't think. But this is actually cosine x. Okay, and then maybe we could have a guess for what h2 would look like. If I set k equal to 1, I get negative, let's see, is this going to be right? Well, before I write it out, let's just, oops. Before I write it out, let's just see what happens. So I'll set n back to 1, put this function in, it's orange, and then we'll increase, and it has the same kind of wobbly pattern. Okay, this looks like the sine function. Okay, so 1 was cosine, 1 was sine. I'll erase the e to the x one. So very cool. Of course, they diverge. They don't go on forever because I only went up to 25. But if I went past 25, it would keep getting better and better and better. So what I could say is, in the limit, this one is cosine x. This one is sine x. And you can get them just by doing sums of powers of x divided by some factorial with a plus or minus thrown in. So that's pretty cool. And the last thing I would mention is these were like the even terms. These were like the odd terms, because these had all like the x squared over 2 factorial, x fourth over 4 factorial. If I wrote this one out, it would have had the x cubed over 3 factorial, x to the 5th over 5 factorial, x to the 7th. over 7 factorial with like alternating plus and minus signs here. So you might suspect, well, if I like interlace those together, we might get back to e to the x, right? Because e to the x was all of those terms together, right? And this one's just, okay, 1 minus that plus that minus that. But the alternating thing's kind of difficult. So this would be like x minus that plus that minus that plus da, 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 da. The alternating thing kind of messes us up. But I could show you one final interesting thing. If you actually took, instead of, so let's say I wanted to add them together, right? So I added one sum plus the other sum. So that would be like adding these two things together, which we know how to do. And we would get something really close to e to the x. If I wanted it to exactly be e to the x, I could plug in, well, this isn't exactly right. Anyway, you get a formula that looks something like this. You have to introduce complex numbers, but e to the ix equals that. And yeah, you can fiddle around with that a little bit to figure out that e to the I pi equals -1, which is a weird result. That's Euler's formula. It's sometimes regarded as like one of the most beautiful results in math because it involves all these different things that you guys are familiar with, like e, pi, the imaginary number I, if you're familiar with it, 1 or -1. Sometimes it's written like this. Instead of equals -1, I could add 1 to both sides, get it equal to 0. So it's kind of a beautiful result in that it actually comes from here. I'm just plugging pi into x. And if you know a little trig, you can work that out. And it does indeed work out to be -1. But yeah, not that you guys need to know that, but it's handy to know the trick for the exponential function sometimes. I think you got a homework problem similar to that, where you wrote out e to the x is approximately 1 plus x squared over 2, and used that to approximate some values of x near 0. So hopefully now you see why it is. It's because this expansion is actually, well, it's actually equal to e to the x when you go out far enough. So there we go. That's kind of similar to what we talked about in section this week. So hopefully that was interesting, and I'll see you guys next week.